Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Uh, Let me introduce myself. My name is Avian Budi. I'm from Electrical Engineering, Institute Teknologi 10 November, Surabaya. Today I will present a paper named Photovoltaic Voltage and Power Cell Characteristic based on Air Quality Index and Pollutant Percentage Level. Okay, let me share screen first. The author is Mr. Sudipyo, me as the presenter, Mr. Budi, Mr. Ramadhani Saputra, Mr. Samsul Anam, Professor Muhammad Azhari, and Professor Adi Supriyanto. Okay, so the presentation outline is first I will describe the introduction and the problem, air pollutant and its surface, including the novelty for the research. And then literature review for photovoltaic and air pollutant level. And then system and proposed modeling methods. And then simulation results and conclusion. Okay, so firstly, introduction and problem. I will try to explain the photovoltaic cells. We know that now there are increasing value on renewable energy used to generate the electricity. That means we also need the exact sizing of photovoltaic since the generated power of photovoltaic depends on the load. In a bad way of doing this, there is another problem besides the photovoltaic sizing. There are pollution in the air that blocks the optimal irradiance going through the photovoltaic gas in this air pollutant, and whether the pollutant percentage level represent how much irradiance that not into the PV directly due to air pollutant. A 10 pollutant percentage represent fully shaded. Fully shaded means code describes as no irradiance response due to pollutant thickness. Okay, and then the paper discussed a more complete description of the definition of the size of PV system with correction to pollutant level and air quality index. Discussion will be carried out modeling using MATLAB. The problem covering the contents of these reports are modeling photovoltaic with no pollutants. Second, we model the photovoltaic with 25% of pollutant, and then 50% of pollutant and 75% of pollutant. And then we can model the pollutant level characteristic. Okay, so we go to the system and post modeling method. The pollutant is modeled with the dust in the pitch surface. Since the photovoltaic installation generally will take place in the pitch in an off-grid system, the dust model sticks to the cell. The irradiance input for the cell will be decreased as the increased amount of the dust. There are specific methods the author used in this paper. Since the pollutant data is abstract and have an open top value, the author simplified the air quality level from 0 to 300 to 0% to 100%, and above 300 as above 100% since the pollution level above 300 is considered as fully safe the photovoltaic modules. So there is no ingredients input for the photovoltaic. And next, as we know, we have the very simple for the formula where there is the current in normal condition E is equal to current short circuit ESC minus EO 0 reverse saturation current times E KV per KT minus 1. Okay, so the first one is we use the electron charge and Boltzmann constant and function of temperature. And then we have to model the simplest model into the series and sun resistant model. We have to include the RS and RP for better approach. So the RS is going here as the amplifier for the current, and then for the RP, sun resistance is modeled as uh, the yes, parallel resistance due to the voltage. Okay, and then we have to model the series and sound resistance model into modified with pollutant level model. The pollutant level model is modified within the pollutant level constant Kp for the amplify for the gain for the short circuit cell current ESC. So that every irradiance input will be modeled as the constant times short circuit cell current or the basic photovoltaic input current. And next we have to design the PV we used. We used the humulus 130 watt peak, and here we have the specification. The type is monocrystalline, and then for the short circuit for the module is 7.25 ampere, and then for VOC open current per cell we have 0.2986 volt, and then temperature coefficient for current short current is plus 0.046% per Celsius, and for coefficient for the voltage open current is minus 0.346% per Celsius, and the RS is tested for 1 ohm, and the shunt resistance is tested in 0.001 ohm. Okay, for the no results, no pollutant, there is X is 0.2446, and Y the current is 6.082. There is the maximum power point, and then for the power voltage characteristic we have the power is 1.488. For 25 pollutant we have the maximum power point at the current of 0.2369, and then for Y is 4.489, and then for the maximum power point is we have the power of 1.076 watts. This is for the 50% pollutant. We have the maximum power point of the current with 2.965, and then the voltage is 0.2276, and for the power we have 0.6748, and then for 75% pollutant we have the maximum current is 0.2106, and then Y is 1.39, and then for the power is we have 0.2927. This is the power voltage and per pollutant level characteristic. So we know that in the very position of the pollutant level, the power per pollutant level beyond the 90% pollutant, the power is going to zero very slowly. But for the voltage, we have significantly decreased. From the simulation, for the 25% pollution, the maximum power generated per cell is 1.076 watts at the point of 0.2396 volts. For the 50%, we have 0.6748 watts at the point of 0.2276 volts. And for the 75%, we have 0.2927 watts at the point of 0.2106 volts. From the research, we know that the pollutant characteristic in affection to photovoltaic cells is constant, and when the sloping per pollution level increase, where the pollution level significantly affect the voltage per cell in a value of 85 to 90%, and rapidly goes to zero. Thank you.